In today's video, we're going to be taking a look at unsolvable, indeterminate, and collapsible frames using StaticsPower. So in our first example, we have a frame that's connected to a pin at the left and then has a roller support on the far right, and we have two forces pushing it towards the right as well as a moment trying to rotate it clockwise. So if we take a look at our reaction forces, we'll have reaction forces at the pin connection on the bottom left, reaction forces between the pins connecting the members, and a reaction force going upwards at the roller. Now, upon close inspection, we see that we have 5 unknowns, being AX, AY, BX, BY, and CY, and 6 equations. So we have 3 that can solve in body 1 and 3 for body 2. So in this case, we have more equations than unknowns, and this signifies that the frame is collapsible. We're now going to use StaticsPower to evaluate the same problem we just looked at in the PowerPoint. We're going to start by clicking Free Body Diagram, and we'll move the screen over so we can see it. So first thing, we're going to change our units into inches, and then we're going to start by putting a 2-point member down, followed by another 2-point member. And now, as we saw in the previous problem, we need to connect points B and D to form a 2-member truss. So something like this. We're going to click pin joint and connect them. So voila, we now have a 2-member joint. Next thing we need to do are add our supports. So we have a pin support at A and a roller support at C. And then we have this truss right here. So we can move it around, we can make it however we want, but since we want it to be like the problem we just looked at, we're going to make it look like this. Now if you want to go in and make the bars a specific length, you can go in and do that down here. In the bottom left of the screen, you can enter in exact lengths for the beams. But for this, we're just going to use it for illustration purposes, so we'll just leave it. So what we need to do now is enter in our forces. So we're going to click our force moment button and click on AB. And we're going to say point force in the X direction and 0 in the Y, so it's going straight to the right. Now it looks like it's going down the length of the beam, but when we hit accept, you'll see that it works out. Now we don't want it at the all the way end of the beam at the pin. We actually want that in the middle of the beam, so we're going to say at about 5 inches. So as we can see here, our force is in the middle of the member going towards the right as we want. Now we need to do the same thing for member BC. So once again, point force, I'm going to say 1, 0 to have it going straight to the right. Use a magnitude of 1. And once again, we're going to put it at a distance along the beam of about 5. So there we go. They're both pointing towards the right and both about at the middle of their respective members. Now the next thing we need to do is add in a moment. So we're going to click on member AB and say couple, put in the clockwise direction, and we'll put it at, let's say, 8 inches. That way it's pretty close to the problem we looked at. So we have everything set up here. Now all we need to do is evaluate it. So we go up here and you see this button that says Exploded View Solve Free Body Diagram. So when you click it, the first thing it says is structure is not statically stable. So this confirms what we already knew about it, that we had too many equations and not enough unknowns. So what this really means is that if we take a look at our structure here, when we apply this loading to it, it's going to want to collapse. The node here is going to move down and these members are going to move towards the right. So specifically this member will swivel and this member will kind of swivel up and over to the right as the beam collapses. So if we take a closer look, if we look at member AB, we have reaction forces AX and AY, BX and BY, our moment and our force. And if we look at member CB, we have reaction force that are opposite of the previous one, BX and BY, another force headed to the right, and CY, or the normal force from the wheel support. So we don't have a balancing force to keep this beam from wanting to move to the right, so it will collapse when forces are applied to it. In example 2, we have a truss structure similar to the one we just solved, except this time there is a cross brace at the bottom of the structure, as well as a pin support replacing the wheel support as in the previous example. So for our reaction forces, we have AXAY at the left pin support, BXBY at the pin joint at the top of the brace, CX and CY instead of just CY at the rightmost pin support, and we have reaction forces at the pins of the cross brace. So for this we have 7 unknowns: AX, AY, BX, BY, CX, CY, and F. And for this we have 6 equations. We have 3 for body 1 and 3 for body 2. In this case we have more unknowns than we have equations, and because of this the frame is unsolvable or indeterminate. So like our previous problem, we're going to use StaticsPower and the free body diagram portion of it to evaluate example 2. So we're going to bring out 3 members this time, connect B and D, and put a pin joint right there. And then we're going to drag this up a little bit like this, move it over here. We're going to take D and put it, somewhere about here. And this, we'll put it somewhere about there. So it looks a lot closer to example 2. So now we've got everything pinned in place like it should be. We just need to add supports. So we're going to add a pin support there and a pin support here. All right. Now we just need to add forces. So on member AB, add about, let's say, point force, and we'll say about 5. And we want it to be heading towards the right, so we're going to say 1, 0. And we're going to put one on member BC, a point force going in the positive X direction. Magnitude of 1 is alright, and we're going to move that to, let's say, 6. Alright, so we've got our 2 forces on there. We just need our couple. So we'll put that there, couple, clockwise, and about 8. Alright, so we have our loading on there. Now all we need to do is press solve. So it tells us that the structure is partially unsolvable. So once again, that confirms what we had previously thought. We have too many unknowns and not enough equations to be able to solve it. So if we take a closer look at it, if we look at member ABD, so the farthest left member, we have AX, AY, F, and then our force loading and our moment loading, and then BX and BY. On member CBE, we have BX, BY, our force loading, F in the opposite direction, and CX and CY. And as we assumed, in the cross brace, we have F going in equal and opposite directions. In our final example, example 3, we have a little bit more complicated of a structure. We have a horizontal member, a vertical member, and an L-shaped member. In the L-shaped member, we can think of it as a 2-force member with forces F running in equal and opposite directions. The horizontal member has 2 forces placed on it, one at the very end and one at the pin between it and the L-shaped member. And the vertical member is pinned between the 2 pin supports with a force moving to the left at about the middle of the member. So with this, we have unknowns on body 1, the horizontal member, of AX, AY, BY, and BX. On the vertical member, we have unknowns CY, CX, and DY, DX. On the pins, we have unknowns F, QY, QX, PY, and PX. So if we total these, our unknowns are AY, AX, BX, BY, CX, CY, DX, DY, PX, PY, QX, QY, and F. And we only know 12 equations, 3 for each. Body 1, body 2, 2 for pin 1, pin 2, and pin 3. So because of this, we have more unknowns than equations once again. The frame is unsolvable or indeterminate in this case. So we're now going to take this and put it into StaticsPower and see if it gives us the same answer. So we're going to start by adding in 2 2-point members and an L member. And we're going to move this point this way to make our horizontal member, and this point a little bit like that. We're going to move, maybe lengthen it a little bit. There we go. And now we have our vertical member. We're going to move this point over here and then drag E down. So now we have all of our members in place. Just need to add in the pins. So we have a pin here and pin supports here and here. And now we have our truss built. Now all we need to do is put in our forces. So we have a force on member AB, and it is a point force at the A side of things, so on the far left, and its direction is good, and we'll hit accept. Then we have a force at this pin, so when we click on the pin, it goes straight to point force, and all we have to do is say in the 0, 0 direction, but in this case 0 minus 1 y, and we're going to give it a magnitude of 1, and there we go, we have that force. Now the last force we need to do is the force here, and we need to say it is a point force in the negative x direction, and 0 in the y, and we want to put it at about the middle, so we'll go about 4. Alright, so we have all our forces on it. Now we just need to hit solve, and it says the structure is partially unsolvable. So once again, it is an indeterminate structure because we have more unknowns than we have equations. So here we have our free body diagram in whole. If you look at member ABD, this matches what we saw before. Member BC also matches, and our two-force member here shows that it is indeed a two-force member with force F going in equal and opposite directions. And at the pins we have our sum of forces that we saw before, and it says here that we have 2 equations on each pin, and 1 equation for this, but 2 unknowns, and 3 equations but 4 unknowns, and 3 equations but 4 unknowns. So just by looking at the number of equations and number of unknowns from here, we can once again confirm that we don't have enough equations to be able to solve this, which makes this an indeterminate problem.